In this presentation, we will explore two common types of lens aberration, spherical and chromatic. We will discuss their characteristics, how they affect image quality, and method to minimize them. By understanding this aberration, we can achieve sharper and more accurate image in optical system. Aberrations are limitations of optical systems that prevent them from perfectly focusing light. These imperfections can cause a variety of issues, including blurred image, color fringing, and distortion. Understanding this aberration is crucial for designing and using optical instruments to achieve the best possible image quality. Spherical aberration arise because a simple spherical lens cannot perfectly focus all incoming light rays to a single point. Rays entering the lens closer to the center converge further away, while those entering the outer edge focus closer. This mismatch in focal point lead to blurred image with a poorly defined focal plane. This slide visually represents spherical aberration. As you can see, parallel rays of light entering the lens do not converge to a single point. The center rays focus farther away, while the peripheral rays focus closer. This mismatch creates a blurred focal spot instead of a sharp image. Spherical aberration can be minimized through various techniques. One approach is to utilize aspheric lens elements. These lenses have a non-spherical shape designed to focus all incoming rays to a single point. Additionally, corrective lenses with carefully chosen curvatures can be combined to compensate for spherical aberration. Doublet or triplet lenses composed of multiple elements are often used for this purpose.
Chromatic aberration arises because different colors of light have slightly different refractive indices. This means they bend at slightly different angles when passing through a lens. As a result, the various color components of white light don't focus at the same point, leading to the color fringes around objects in the image. This reduces overall image sharpness and introduces color artifacts. This slide illustrates the chromatic aberrations. As a white light enters a lens, it separates into a concentrated colors, each with a different wavelength. Since each color has a slightly different refractive index, they bend at various angles when passing through the lens. Consequently, these colors don't converge at a single point, resulting in the blurred image with color fringes around objects. The fringes appear because the different color components are focusing at slightly different planes. There are several methods to correct chromatic aberrations. A chromatic lens composed of two elements with different dispersion properties are a common solution. These lenses are designed to bring two specific colors, typically red and blue, to a common focus point. Approach chromatic lens takes this concept further by correcting for three wavelengths, often red, green, and blue. This results in even less color fringes and sharper image across the visible spectrum.
Additionally, employing low dispersion material in lens constructions can minimize chromatic aberrations. These materials have a reduced variations in refractive index across different wavelengths, allowing them to focus various colors closer together. Forward and specific type of extra low dispersion glass are popular choices for low dispersion lenses. Spherical and chromatic aberrations are both imperfections that occur in lenses and can affect image quality, but they arise from different causes. Spherical aberrations happen when the lens itself is quite the light shape, causing light ray to focus the slightly different spots, blurring the image especially at the edges. However, chromatic aberrations doesn't care about the lens shape caused by the material properties of the lens. Different color of light have different personalities. Some have shorter wavelength, while others are longer and more relaxed, and bend at slightly different angle when they pass through the lens material. Spherical aberrations result in a blur effect, especially noticeable toward edges of the image. However, chromatic aberrations is create color fringes around object in the image, and there are two types of chromatic aberrations that arise due to dispersions: lateral chromatic aberrations and longitudinal chromatic aberrations. In collections, spherical aberrations can be mitigated by using a smaller aperture or by using specially designed lenses or more complex shape. However, chromatic aberrations can be corrected by using achromat lenses, which combine lenses made from different material with different dispersion properties. Spherical and chromatic aberrations are inherent challenges encountered in optical design. This significant influence image quality produced by lenses and mirrors. Spherical aberrations affect image sharpness by causing variations in the focal point of light ray entering different zones of the lenses. Conversely, chromatic aberrations introduce color fringing due to the varying reflective of different color wavelength. Corrective measures such as using a spherical surface, combining lenses with different curvature, and employing specialized material are essential for minimize these aberrations in the optical system. In this presentation, we expose spheric and chromatic aberrations, two common limitations in optical system. By understanding these aberrations and the method to minimize them, we can achieve superior image quality in various applications. If you like to delve deeper into this topic, we have a reference list here provide a comprehensive explorations of applied optics. I hope this presentation was informative. Thank you for your attention.